exhausted last week.
Hey, Michael.
There were things in class that happened that it was like,
No, that's okay. And it's a hard question. I mean, it's like once you realize what's going on, oh, it's simple. But these are one of those things. If you know it, it's cool. But
it's
it's easy.
trivial.
Yeah, but then unless you know it, it's not obvious at all. So, Jordan.
Hello.
No. Oh, here. Where is everyone? I'm early. No, I'm not.
no,
I'm fine. Moses is also missing. Oh, I can go down.
okay. So I was curious about that, it being 1, because of what we were doing in class, but I thought maybe we were taking out the approximation for the letting it be 1.
No, it's always 1. So it's kind of much more simpler than what you did. So,
Oh, okay.
so what you did is completely correct. It's just, it's simpler. Hello, Alia. Huh, there are 1, 2, 3, 4. I think it's Moses and Luke. Oh, here you go. Moses is very late. Okay, let's proceed. So before we proceed, Rob brought this up.
Not to blame.
Yeah, it's perfectly sitting there. Yes. So Rob brought out that he was working with one of his students on some programming, and he said this was what was mentioned in the class, and he points out that in Erskine this is k raised to n, not k raised to 2n, which is off. That's not identical. They will be different. Right? As simple as if you put k equal to -1, this is an even, this is an odd function. So surely they are not the same. And yeah, so what do I say? Okay, I don't want to say that I'm right and Erskine is wrong. That's too big a claim.
The one thing that I'm looking at it from a distance now is I wonder if they messed up where they put their bracket.
Oh, so you're saying k should be here and everything is fine.
Because
Yeah.
they printed it on, I mean, if the version I had was printed on the outside of the bracket.
Sure.
But if that was a typesetting issue.
Sure. Sure. But as it sits, okay, so here is whenever these kind of things happen, I don't want to, I mean, I wouldn't trust myself that this is correct. So that's the best way to proceed. So there is this, what is called DLMF. This is digital. It used to be a huge book. These days it's digital library of mathematical functions. it is maintained by NIST, which is National Institute of, what does it, ST stand for? Standard, some standards, like wherever, like it's American, for example, who sets his units, right? kg, kg meters and seconds on. So the National Institute, NIST, it's in Colorado, right? Okay, I don't know. Sorry. Yeah. So look this up. So that's it. That becomes a quiz. Here you go. So, you're much more prompt when you're online.
What?
It's easier to be prompt when you're online.
Yeah.
Okay. So the quiz is to find out which one matches with this, and we stick with this, I guess. Then you can always ask, why should I trust this one? Yeah, then you have to go back and look into your equations and see some similarities, and that's the only way that becomes a research problem there. But I should point out one thing in here, which is very close to what the issue between this. So Mathematica has a similar problem, but it's not wrong because it, so remember K was introduced this way, right? Let us say K, right? So this is 0 to pi by 2 d psi 1 over 1 minus K squared of sine squared theta, sine squared psi. Okay, that's how we define our K. But so this is class actually, so this is what classroom, and this is how traditionally everyone does. But Mathematica decided to change this notation, and that leads to a confusion very similar to what is there on top. And I wouldn't be surprised if Erskine used Mathematica to get the series, and then you get a different series. So this is Mathematica doing it, and Mathematica being very used by many people, that leads to a significant deviation. So Mathematica defines exactly K, the same K, everything is the same, but it decides to write a 1 minus K sine squared. Or maybe this still stays the same. It says this is K squared. I think that's how it goes. So when you implement K, Mathematica's K, it is actually put, so for example, what should I do? Let me say this is equal to, Mathematica has this elliptic K. Elliptic K, that's the function. When you call it as K, it is actually just this. They would explicitly say K squared to get that. You see this? Mm-hmm. And that seems to, so if I now take this function of Mathematica, am I in the, so if I were to work in Mathematica, start from here and ask it to take a series of this, and it will give me a series in K. But the understanding is that, I should be putting it as K squared. So this seems to be related to this, but maybe one should be careful in saying anything.
That would make sense as to why my number was low. For
Yeah.
my,
Okay.
Because so if I, by Mathematica, I was actually, what I was looking for was the approximation for little k equals 0.8, but mathematically give me 0.64.
Okay, check it out. But this should be easy to fix, right? And I think, and check on it. I think the best is to plot it, right? Or plot this minus this somehow, like elliptic k minus this, right? Like write this as an explicit integral and then subtract out and make sure that it's 0 for significant 10 digits or something. So I think that's what I would suggest. Yeah. Does that help? I think, yeah. Let me know whatever happens. I would like to know. If Erskine is wrong, that's, yeah, it's a popular book. I think it was Jordan, you pointed out that I used to use, I used to say the elliptic integral of the first kind and second time for quite some time I was flipping it. I think it was Jordan who pointed that out, was using it. Yeah. Okay. Is that, shall I keep it there and move? Not a resolution, but that's like that. Okay.
This was one of those things that when I was supposed to be working on one thing, I got distracted, went down the rabbit hole.
Yeah.
And then come back and say, oh, I need to get stuff done.
I try to say this often. I mean, earlier I used to be very prompt at saying that I guess I missed it. And if you come across this, then you can spend days on this. If you're in a serious program, you know my answer is not matching and know that it has to be there. So you could spend a lot of time there, unnecessary time. So that's why you should be careful in changing notations. That's one thing, especially traditional notations. And it's very common, everyone does it, including me. Like often it is that you have piles of nodes you have built and you have built it using one notation. And that is the whole library sitting out there. And it's easier to use your nodes. But you should be considerate that if you get popular, people will start using your nodes. And that could be a lot of error. It leads to a lot of errors. Okay, you'll come. Okay. So homework 6 and 7 is all postponed in a sense. 6, 7 is, but when is it due? March. It says March 16 for me, but I think I made it due 25th, I think. Yes. And midterm 2, this is, oh, that's not very far away. Not really. That's next week. Oh, and we also said this is in class. Okay. By Thursday, I will decide something clearly. Oh, no, as of now, no, I might change my mind. Because I have this advantage that I might get to teach on that also if I make it take home. Okay. So anyway, I'll decide on that. So there was this question on about an electron and proton coming. Electron, proton. So this is actually, it is shown like this, but it has a meaning, right? And there's a photon that is, so think of this as an electron. It is negatively charged, and a positron, which is basically an electron with a positively charged, and this comes and collides with each other, and they disappear. These two disappear, and there is a photon that comes out of it. Surely it has to be in the same direction, otherwise the momentum and this direction cannot be conserved. So, because if I were to show as I pictured it out there, that means horizontal momentum shows up suddenly. So this has to be in this direction. Photon has to be in this direction. And I said that's not possible. Right? And Moses, you gave the right answer. I think your answer was good.
You read my submission already?
Yes, yes, I was
Okay.
curious.
Yeah.
And so it's a kind of a nice argument. Moses, you want to say?
Sure. Well, I basically said that, I mean, the way you drew it in the first case, the velocity vectors of the electron and the positron, well, they have to be less than the speed of light, so they have to be time-like vectors, which means that you can choose a reference frame in which they're purely time-like. So you can basically get rid of any spatial component, any like horizontal component of the velocity. So then in order to conserve angular momentum or linear momentum, in order to conserve linear momentum, you need, you can't just have one photon coming out. You'd have to have one going in the opposite direction.
Yes, that's correct. So just a simpler version of it, exactly what you said, but in slightly different words.
Yeah.
There is a center of mass of these two frames, right? That moves, correct? So instead of thinking of these two particles coming into each other, think of there is a center of mass. If they are the same mass and if they are the same velocity, that's pretty much at the center. But don't even think of same as a center of mass frame. Sit on that frame, right? Its linear momentum is 0. So there exists a frame, that's what Moses was saying, there exists a frame in which the initial particles have 0 linear momentum. Is that clear? Because they have massive, it is possible to do that. There is a center of mass, it is 0. But after the collision, there is only one photon. So linear momentum has to be conserved, so the photon has to be at rest. Right? But the photon can never be at rest. So it's not possible. Just, is that clear argument? Any questions? No calculation, it's kind of neat. There were similar arguments at the end of the last lecture, and I felt maybe I was hurrying, or maybe it was not going through very easily. Do you want me to repeat that? Has anyone gone through it? Has time to go through it? Or?
I looked at the notes from last time,
Uh-huh.
and near the end of the lecture, I don't think I could follow.
Okay, so we can try to tell it in a different words, maybe. Yeah, okay.
So can I interrupt real quick?
Yes, please.
Regarding the exam, well, I'm just recalling that Jordan had to take off work.
I know.
So-
I had to decide due to that reason, right? Jordan, have you taken off work?
I haven't yet, because you've kind of mentioned over
Okay.
and over that you're not sure, but as of now.
Yeah.
So I was just kind of waiting for you to
Yeah, so can I decide
your
on
mind.
Thursday? You don't have a choice.
What's that?
Is
Sorry,
it-
you were cutting out.
I decide on Thursday that whether I'm going to have a class exam.
Yes, yeah. Hmm.
Anyone else
Yes.
affected? Rob? Yeah. Rob, you anyway come, right? Yeah.
I'm here anyway. so-
Yeah. Yeah. So, yeah, I'll decide. What do you guys prefer?
Doesn't matter to me. I'm going to be here in person anyway.
Yeah, I'm gonna be here anyway.
So no preference. Whether midterms here.
I mean, there's a preference for me, just because I would get to work and then I wouldn't have to work extra hours on the weekend. But obviously, if you had it in class, that would work as well. So
So you will have to work extra hours if you take off. I thought you were the owner of your own business.
Yeah, but there's like a list of things that have to be completed, and those things have to be completed in a certain frame of time, or no photons are emitted. And those photons are money that I need.
It's not like the homework that you can postpone or just skip. Aliyah, preference?
No. I
No
think
preference.
that-
Okay.
Yeah.
Yeah, let me decide. I'll do this. Yeah. I'm not able to make a comment.
Yeah, I think the only, I mean, this is my perspective because most people here are recently out of their undergraduate, and so there are things that have slipped my mind. So sometimes it's having that time to go back and figure out, okay, I'm missing this, so let me go back and look at that. I mean, that's one of the benefits to
I know.
For a take-home exam.
For a take-home.
Right, but the Zoom versus in class, those are nearly the same, right?
Yeah, nearly the same. It's if I allow it on Zoom, there is no difference there. But it's
Okay.
just that I'm making a time. I'm making a time limit here. That's what I'm trying to say. Okay. So the point is that sometimes what happens is that, like I ask you, what is the electric field due to a spherically symmetric conductor, like a charged conductor? I expect you guys to be knowing out of the mind. That's an expectation I have. And that kind of assessment doesn't come out of take home. That is my only thing that I miss. And most of the time it is okay, like it's fine. I don't get to do too much. But I think in the first midterm, I got this feeling that, this is not okay kind of thing. So I think at that time, I was very much wanting this. But now I think I forgot about the whole thing. I'm not keen on it. Yes, Jordan.
I think one of the things that, that you did on the first exam is you allowed communication between parties in the class, which I think is a good thing if, that's, it's obviously it's helpful to talk to each other and work together on certain ideas, or if you're stuck on something, but maybe on some take-home exams, it might be beneficial to not allow that.
Yeah, I know. Okay, let me take a decision here right away, right?
Okay.
Spontaneous decisions, right?
Well, it can still be, I guess, like my point is, it can still be an in-class exam,
But
with a time limit, but
allow Zoom.
Yeah.
That way, you're talking for Jordan.
I mean, he's the only one that makes a difference.
Yeah, I understand. Okay, so surely Zoom allows, but I'll just make this take home. Okay. Since you guys you think I am unreasonable, so take home.
I don't think any of us are saying that.
No. Or you think that is reasonable to do that instead of saying I am unreasonable. It is reasonable to say it's make it take home and Zoom, or you're saying make it Zoom. That's your point. But I'm extending it to take home. Right? No time limit. It doesn't matter so much because there's so much error bar in the grading anyway. So I don't think I have much problem in this class. Yeah.
It's more for us.
Yes.
I would, if it's an in-class exam, I would prepare more for it. If it's a take-home exam,
Okay.
I'll prepare less.
I hear you. I hear you. Okay. We have a in class.
Sorry.
in class Zoom allowed, right? Okay. Fine. Blame it on the process. So in class time constraint, okay? So this is time, fixed time. So it'll be a short exam, short questions, but fixed time, 1 hour and 15 minutes. No room for a little bit here and there. It's okay, but I'll make it short enough that it shouldn't need that. Okay. And I'll be lenient. Okay, reasonable. That was fine.
It's probably not a bad idea for those of us who are in quantum mechanics, because next week we have an exam in his class, and
But his exams are very long, very long.
uh,
Dr. Bird's exams are long and tough. So
Yeah.
It's gonna be a disaster.
that's yeah, my exams are too easy, I think. I spoil you guys. Okay, let's study half an hour. Okay. Okay, so we were doing relativistic and what we said is we defined ds square actually minus ds square equal to c square minus x dotted with x. That's your definition of invariant distance ds. It's convenient to write this as ds square is c square dt square and 1 minus that's velocity. So that's 1 minus beta square, so that's gamma square. So that's c square dt square over gamma square, right? 1 minus beta square. Gamma, remember, was 1 over 1 minus beta square. Oh, something wrong, right? It's wrong. I changed my notation. Yeah, because you.
Working out a dt squared.
Again, yeah, here this is off, right? We go by the democratic place where more space gives plus. I think that's correct. Yeah. And that's minus. So this gives the ds is equal to c dt over gamma. Okay. So the idea is that instead of time, it's often convenient to think in terms of infinitesimal distance, which is actually invariant with respect to frames. You can go to any frame. And that can be the first point. The second is we defined x mu, right? A fourth position, if you want. And that's a general theme you want to have. Whenever we want to talk about physical quantities, we want to construct 4 quantities, if you want, 4 vectors. So x mu, whenever we want to talk about position, c dt So this is x mu is actually x0 and x vector x, which is the same as c dt. So x0 is c of dx means of ct dx means sorry. dx mu dx naught dx. That's c dt, and I don't think this is how we did it, right? I think it is better to say x mu is equal to x0 times vector x. And that's the same as c times t and vector x. The same time that we are used to and the same position that we are used to, but the combination of them has this interesting feature that the square of the spatial components minus the square of the time component that stays the same with respect to any frame. And by any frame, I mean something that is moving with respect to the other with uniform velocity. Right? That's pretty clear. Then we define what is called for velocity. For velocity, now this is a definition we need, because velocity we know what it is, but for velocity we use the idea that this does not change with respect to who is measuring it. So what we say is that let's define delta x mu. If we divide it by time, then time itself transforms. So do this ds, because that doesn't change from frame to frame. And delta s tends to 0, which is basically dx mu over ds. Define this to be u of mu, or let's say alpha. Alpha doesn't matter. But then we have this issue that we would like to associate it with velocity. This is a distance that's also a distance that's not having the dimensions of velocity, so multiplied by c. Multiplied by c here, multiplied by c. This quantity, we showed that if I were to do this, this is c times gamma, because I get dt by ds, and dt by ds is gamma. So we get c times gamma there, and velocity times gamma. That was your for velocity. And while doing that, we also showed that u alpha, remember, any time you do two 4 vectors and do this construction, this will remain the same in different coordinate systems. By different coordinate system in different frames, different boost frames. If you're moving with any velocity, this quantity will remain the same. Like whoever measures it will come out to be the same. And what is that equal to? In this case, this we showed is equal to exactly c squared. Right? So c squared. So again, maybe 2 steps, right? Just to clarify, we did this, but still u alpha. So I made a subscript instead of a superscript. That's got by minus c gamma, and velocity v gamma. So u alpha, which is expected to remain invariant. By invariant, I mean it doesn't change from frame to frame. So that's minus c squared gamma squared plus v squared gamma squared. I can take a minus c squared out, and I get, oh, so this is gamma squared. So gamma square can also come out, so it's 1 minus beta square, and we notice that that's exactly equal to 1. So this is equal to minus c square. That suggests that this is time-like. So this implies that u alpha, or for that matter, it doesn't matter whether you talk in terms of superscript or subscript, u alpha, which is a full velocity, is a time-like vector, 4 vector. But that doesn't mean that it is of the kind of time. Notice this is a velocity vector that has nothing to do with time. Right? Velocity will have a 0th component and 3 spatial components, but that doesn't mean that this should be interpreted as time. It is not the time variable at all. It is just the 0th component of the 4 vector. And there are space components, or we call it the space components of the 4 vector, or you can say 1 to 3 components of the velocity vector. And that's a time-like vector. And that has the implication so u alpha is equal to c times gamma and velocity times gamma. Gamma, remember, is 1 minus beta square. That's in a particular frame we are talking about. If we are having a frame, if I change the frame, I say let's call this u bar. That's another frame. C gamma bar, let's say. This is velocity v bar with a velocity vector, and that's gamma bar. Is gamma 2 bothering? I mean, this looks like v by v and gamma. I think contextually, hopefully it helps. If I go to another frame, so this is power C gamma bar or v bar. Is that clear? Okay. So I can have many such frames. Each one is going with respect to the other with a uniform velocity.
Is
Yes.
the gamma next to the C of bar bar?
Bar, yes. Yeah, thank you. Okay. Now, how does this look like in a, we call it the space-time diagram, but this is need not be space and time, right? Now we are plotting a u here. So let's say magnitude of u here, so u vector u. By that I mean 1, 2, 3 components, and I take the magnitude of that. And this is u0. Again, I stress that this is not time and space. Now, how does this look like? I said that this is a time-like vector, so it has to be either in this cone or in this cone. That's what it means by it's a time-like vector. It is in one of these 2 cones. It cannot be in this cone or this cone. So let's say it is going in the positive direction, and this could be your u alpha here. That's your u alpha. If I change my frame, I change my components. It is like if I rotate my coordinates, x and y will change, but the length remains the same. By length remaining the same, what it means in this Minkowski space is that its head has to stay on the curve. Right? Instead of staying on the circle, it has to stay on the hyperbola. And now this could be your u bar alpha. Somewhere else could be your u double bar alpha. It's another frame. You have u double bar alpha. And you can think of many such frames. Every frame is on that hyperbola. Is that clear? out of all this, I can choose one. This one, this is a very special frame because there it doesn't have this. This is equal to 0. Right? So let me, no, I do. Let me call this U tilde. That's a special frame. So there is one such frame which I'll call, oh, this is all alpha by the way. U tilde alpha is special, right? So that's that vertical one, which is what, so what is that equal to? It has this space component 0 there. Right? So this is equal to 0. And this is equal to C times whatever this is, gamma tilde. Right. But what does this mean? If this is 0, remember what is this equal to? In this particular frame, you have V tilde divided by 1 minus V tilde square over C square. Right? That's what this means. This is equal to that. If this is equal to 0, how can I have this to be 0? How can I have this to be 0? I think V has to be 0, right? Is there any other possibility? If V goes to infinity, or V goes to C, that's 0. So that's infinity, right? So the only way to get this to be 0 is V going to 0. So this implies, so this equal to 0 implies that V tilde is equal to 0, correct? Which means that you're in the rest frame, right? So this means that you're in the rest frame. If that is the rest frame, that means V is 0, that means that's 1. Right? So this is equal to, actually, this is C and 0. And you can use this argument for any time-like vector. Out of all these possible frames, you can pick the one that has this vertical component alone, which means that this is all gone to 0. It need not be the rest frame in an arbitrary vector. In this particular, for the velocity vector, it comes out to be the rest frame itself. But for an arbitrary vector, for example, if you're talking about let's say electric field, electric field is not a 4 vector. Electric potential, right? Scalar potential and the vector potential turn out to be a 4 vector. And you could ask what is happening there. This is information I'm giving you. So we have seen the scalar potential and the vector potential, right? This turns out to be a 4 vector, right? It's neither a vector. We found that this is actually a vector, right? A is a vector and that's a scalar. But under Lorentz transformation, it is neither. It is neither a vector nor a scalar. It's a 4 vector. Exactly like velocity. Is velocity a vector? Now suppose I were to ask you, is velocity a vector?
It's a 3 vector in real space.
Very good. Yeah, so the answer is not that it is not a vector. So you would say that, oh, you didn't specify the cushion correctly. Right? You have to ask, are you talking about 3-dimensional space under rotations? So when you ask something is a vector, the question being asked is under rotations, what happens to the vector? How does it transform under rotations? If it transforms like a vector, let's say like the typical position vector in 3-dimensional space, then it's a vector in 3-dimensional space. Seems like it's a tautology, but it can be made more precise. Usually you say it should transform like a gradient operator. So the more correct definition is anything that transforms like a gradient operator in 3-dimensional space under rotation is a vector. So now when I say is A a vector, yes, it is a vector under three-dimensional space of rotations. But under Lorentz transformation, which is in 4 dimensions and which has its own transformation, then A is not a vector. These are 3 components of a 4 vector. And overall, together phi and A is a 4 vector under Lorentz transformation. Is that clear what I roughly said? Okay. Should ask or critically think over that. Okay, if that is the case, so now we have I have hopefully convinced you that if there is a time-like 4 vector, especially the 4 velocity, then I can go to a special frame where it is exactly this. So let me stick to that special frame. In that special frame, we, by the way, we also showed, recall that what we did was starting from u alpha is equal to, right? This is equal to 0 because when I take the derivative, it becomes the acceleration, right? So this implies that u alpha, am I within the, yeah, u alpha, a alpha is equal to 0. Is that clear? We showed this. This is just 2 steps from here to there. Right? Maybe just to, because I can hit on this du alpha over ds, u alpha, or the second one, right? U alpha times du alpha over ds is equal to, this is also equal to minus c squared, that's equal to 0. That's defined as the acceleration. That's also the acceleration. That implies that this is equal to 0. Okay. So we have the product of 4 velocity and the 4 acceleration to be 0. If a 4 vector multiplied by the 4 vector is 0 in one frame, it has to be the same in all frames because this is Lorentz invariant quantity, right? Whenever I like, it's like u alpha will be Lorentz invariant. I can go to any frame I want to. If I now go and analyze this in my special frame, right? I chose tilde. That's also correct. So now I am in the special frame. If this is true in one frame, it is true in any frame. Go to that special frame. What does it say? U tilde alpha is equal to 0, sorry, c and 0. But in that frame, acceleration need not be 0. Let's put it at the bottom. I don't know what's going to be the acceleration. That's a different vector altogether. Remember, acceleration, if velocity is 0 and acceleration is derivative of velocity, should that be 0? If velocity is 0, acceleration is dv by dt, right? If v is equal to 0, is acceleration 0? Not necessarily. An example?
Throwing a ball up in the air at the very height.
Good. Throwing a ball up in the air right at the top, it is not 0, so acceleration need not be 0. So we don't have to conclude that at all. So we don't know anything about the acceleration. So in general, I will have a tilde, let me call it downstairs, and there will be a vector for A. So when I take the product here, so I get C times A tilde A naught, and minus, also this is minus, plus 0 times vector A, 0 dotted with vector A is equal to 0. But it doesn't matter whether this is 0 or not. The product is 0, so this implies that minus C times A tilde A naught is equal to 0. So tilde 0 is equal to 0. Correct? In that particular frame, not every time, right? But now, what can I say about, so in this particular frame, I know that this is equal to vector A. But what can I say about the magnitude of A alpha now? In that particular frame, if it is calculated in one frame, this remains the same. That's equal to magnitude of A square. So that's minus 0 square plus vector A dotted with vector A. That's positive, which is greater than 0. That means this is space-like. Right? So we have concluded that acceleration is space-like. So A alpha. So once it is space-like, I don't care. Then I can release my frame. I can go to any other frame. So if I were to plot this here. So now I'm in the acceleration components. This is the 0th component of acceleration, and that's a spatial component of the acceleration. Since it is a space-like quantity, so it must be here or in this frame, especially since in this particular frame, this is here. The pure space region, 0 component is 0, so that's horizontal there. And if I move my frame, I can go anywhere on this. I can be here, I can be here, anywhere. But it's the same acceleration vector we are talking about, but as measured in different frames. So what I've concluded is that A alpha is space-like. Is that clear, the argument that went through that? That
I think
place.
for me, it's clear.
Yeah, go
I
ahead.
think for me, it's clear. It's clear what you're saying, but like I'm following exactly what you're saying, but from like a visual perspective, I guess I'm struggling a little bit.
Yeah, and I would say that that's expected. So that is what I think everyone says. This is so new. This is not so counterintuitive, or I wouldn't say not even counterintuitive. There is no intuition to help here, right? That velocity is time-like, acceleration is space-like. There is not much intuition there. So you have to build the intuitions like this. As you keep working on these problems, you build your intuition here. That's the way to say it. Does that help at all? So I'm not surprised at all what you're saying. It's expected, or it will be surprising if it comes out to be very comfortable. It's not supposed to be comfortable. You're not seeing these things before. But these kind of arguments is very common in relativity. Maybe that's the way to put it. Like this is how you would show, and very common. Even when you talk about a black hole, for example, after this, if you think you have captured this argument clearly, go and look for how does someone who is falling into a black, how does he interpret time? Like typically the question asked is, you're falling into the black hole, and let's say your legs are going first and your head is going, so you're radially outward, standing radially outward. So your toes are closer to the black hole than your head. So you can make it the other way also, it is just more complicated. So radially when you're falling in, it helps. And now the question is, will you see your toes getting into the black hole? Is that possible? Remember that black hole has this has a very surprising feature that light cannot escape from there. So this is how the questions begin there. And these kind of arguments are needed. So basically you go into the rest frame. So that always in relativity, you go to some frame. So the one who is falling, you go to that rest frame. but the head is slightly away from the toes, right? So the rest frame of the toe is not necessarily the rest frame of the head. Remember that you're going to be stretched very hard, like black hole is pretty strong, so the tidal force is significantly, and the time dilation that also, this is all, I don't expect you to be aware of all these concepts. When the tidal force is very large, the time dilation is significant. You might have heard that in the time in our satellites is slightly different from the time we are used to here, right? And that's because there is a gravitational difference, difference between the gravitational force 300 kilometers above Earth than it is here. And that tidal difference, that's what is called the gradient of the gravitational force, that causes time dilation. Here we are talking about reference frames. There in gravity, we talk about time dilation due to change in gravity. And very close to black holes, this time dilation is large enough. And then you have to talk about what kind of time dilation is it? How does this affect an observer who is falling? And there are counterintuitive results you get, and there you use a similar argument. So yeah, maybe I can give a quiz. Just read, I mean, don't spend too much time, like 5 minutes or something. Look for time for a person falling into a black hole. It's not even special. Versus time for a stationary observer. There are very paradoxical conclusions you can get there. So just look it up, it might be interesting. So that's, I can say. Where is this? Where is
Oh, yeah.
Okay. Okay, so with that feature, let's proceed ahead. So now what we have is, again, x mu is equal to ct times vector x alpha. Alpha is equal to c gamma and v gamma. And acceleration, we haven't, this is a time-like vector acceleration. We did not really explicitly write it. We said this is going to be alpha over ds. So let us get an explicit expression for this. So this is equal to, like we did earlier, use a chain rule. Oh, we should again make it at the dimensions of acceleration, right? Because this is a distance, that's a velocity, so let me put a seed. The distance cancels out, and that's time. So this is the same as d, so put it in there, right? So it is c times d by ds of c times gamma, so that's c times gamma, and this is d by ds of v and gamma. This is standard simple derivative. I just took it inside. Clearly, there are many places it can hit. It can hit the gamma or the velocity, or it can hit this. Make it a chain rule. So this is c squared and dt by ds and d gamma over dt. That's the first piece. The second piece is c times dt by ds, and d by dt velocity and gamma. That's gamma. Remember c times dt over ds was gamma. Right? That was something that we saw earlier. So that's equal to, that's a gamma now. So c times dt, so this is c times gamma times time derivative of gamma times c times dt, this is gamma, and this has been collected. This one now I'm going to distribute, right? This is derivative of velocity with respect to time times gamma, not hitting that, or I can hit the gamma, so this is gamma velocity time derivative of gamma. Okay. Let's just algebraize this way. Let me connect this together, and this is our usual velocity, right? The derivative with v, the usual velocity with the usual time. That's what you would measure as acceleration in a frame, in the usual lab frame, let's say. So that's acceleration. So let me define this. This shouldn't be confused with the force acceleration. That's equal to your usual acceleration or Newtonian acceleration, if you all want. Before this, I should have done something. Okay. Yeah, I'll come back. The good part I forgot. Okay. Okay, so that's acceleration. I still have time, right? Because you guys allow me to take extra time. It's okay. So this is in terms of the acceleration. So this is c times gamma by dt, and this is acceleration times gamma squared. Yeah. So this is acceleration times gamma squared plus velocity. So there is, notice the spatial part of this force acceleration has a direction in the velocity sense and an acceleration. So this is slightly more involved than the usual acceleration. So it's not just acceleration getting dilated or contracted by some factor of gamma. There is, its direction itself is changing. It has some velocity piece in this. So that's your for acceleration, and we would like to get this part now, but that's it's not very clear how to proceed when one can explicitly do that. But we'll use a trick to get this d gamma over dt. So to get that, we use the fact. So once I get this, then I have the expression for acceleration explicitly. So, so let's do that using the fact that u alpha, a alpha is equal to, this is a time-like vector, that's a space-like vector, and that's equal to 0, is that right? This product is equal to 0. So if we have this expression for u and a, that means I have a relation there. So just use that. So it is c times gamma, and then minus of this. So this is minus of c times gamma times d gamma over dt plus the 3 component of velocity, which is velocity times gamma, dotted with acceleration 3 component, which is a Is that clear of how I got this? Right. This is U0. Or let's say this is minus. This is the 0th component of U. That's the 0th component of acceleration. This is the space part of velocity. That's the space part of acceleration. Is that clear? Especially for those who are online, because it's not on your board. Jordan,
I
Christian?
think so. Yeah.
Thank you.
No, I got you.
Good. Okay. Yeah. Alia? Shall I proceed?
Yes?
Yeah. Now I said, shall I proceed? Any questions?
No, thank you.
Yeah. Okay. So notice that gives me a relation where I can solve for d gamma over dt. That was something that was stuck there, right? How do I proceed with that? So let's collect things together. Let me collect the d gamma. Let me write this as c gamma square gamma by dt. We expand this plus v dotted with acceleration times gamma cube, right? Plus, this is v dotted with v, those are the vectors, so that's v square, gamma square, and d gamma over dt is equal to 0. So that tells me that minus c square, gamma square, 1 minus beta square, right? These two combined together with the same feature that we saw earlier. D gamma over dt plus v dotted with a gamma cube is equal to 0. What is the quantity in the square brackets?
1.
That's exactly equal to 1. So I learned that the derivative with respect to gamma is equal to v dotted with a. This has the dimensions of time. So O divided by c squared times gamma cube. That's an identity if you want. One could have calculated time derivative of the Lorentz factor if you want the gamma explicitly, but we use this trick to calculate that. So just a simple trick. Right? So we now have this. We can now substitute this back in here to get the expression for the acceleration clearly. Right? So the acceleration then is, so if I were to write it right here itself, to do that here. Right, so that's, remember, acceleration. For acceleration is equal to, I just have to substitute this there. Right? So this is c times gamma raised to 4 right, times v dotted with a over c squared and we have vector a square plus velocity times velocity dotted with acceleration over c squared. Notice this is the vector, it's in the direction of velocity And there's a gamma cube, which is gamma, which makes it gamma 4. That's your acceleration in the explicit form. We will come and process this and talk about. Notice that is sometimes it is in the direction of acceleration, sometimes it's in the direction of velocity, and especially if it is linear. So this has this interesting feature that if you had a charge in an electric field and the charge is starting from rest, then the velocity and acceleration are in the same direction, correct? A charge in an electric field, if the charge is starting from rest, its velocity will start from 0 in the direction of the electric field, and it will accelerate in the direction of the electric field, right? So velocity and acceleration are in the same direction when a charge is in an electric field starting from rest. But if it's in a magnetic field, velocity and acceleration are perpendicular to each other. So that plays an important role here. And in what sense does it play a role? One is related to gamma square and gamma raised to 4. So you can ask, is the acceleration how much does it get Lorentz factored? Like when you're talking about a distance, it is contracted by a gamma. Time is dilated by a gamma. What happens to acceleration? What kind of factor does it come in? And we will see that electric and magnetic field behaves differently. But that's, we'll postpone that for the next class. Here, I want to talk about the main crux of relativity, and that was in between. Right? After velocity, I went ahead and started talking about acceleration. That's perfectly fine. That's how you would do in Newtonian physics. But in relativity, it's good to define momentum in between. Right? That is, momentum also comes in, and it is just a nice thing, and it plays a very crucial role. As of now, I haven't changed any Newtonian physics. No. Acceleration is the Newtonian acceleration, velocity is the Newtonian velocity, everything is the same. But it is the momentum where things change, and that's where Einstein played a very important role. So let's do that. So that's what I said, I forgot the main part in that. So let's define what is 4 momentum. So as when it comes to 4 momentum, that's just a definition. So this is not there in Newtonian physics at all. But we will define this P alpha. So that's a 4 momentum. Will be defined as mass times U alpha. Where M now, I have to say what is M, or let me not say what M is. Let me keep it open, because one might ask, what is M? Does it change with reference frame or not? Let's leave that alone, and I'll come back to it, and we'll see how M changes. It's going to remain a constant. So what is this explicitly? So this is the same as U alpha is MC gamma, and this is MV gamma. Now this is where the connection with physics comes in. So this is physics now, next step. Okay. So this is physics if you want. Okay, that's what Einstein did. He saw this observation. He said that this is actually momentum, not the, so remember that we define momentum as mass times velocity in Newtonian physics, but Einstein said this is P. Let's call this Einstein. Not the Newtonian momentum, right? Newtonian momentum would be the Newtonian momentum is MV. How about that? This is just P. That's going to be our P. Let me not call that Einstein. That's our P, but P Newton is MV. So P is equal to P Newton times gamma. So that's a definition now, if you want, or connection with physics. And that leaves us with the component here. What is that going to be? So you would say this is the energy. But then it has to have the right dimension, so I put a C. And this is, so this is again not the usual energy. This is not Newtonian energy. What is Newtonian energy, by the way? Newtonian energy. So if momentum is mv, what is the energy? There's no interactions in here. So the only energy there is kinetic energy then, right? If there is one particle, we're just talking about one particle here. Right? It's not interacting yet with, it's just kinematics. So it's half mv squared. So, but then the question comes, what is the connection between relativistic energy and the Newtonian energy? That's we'll come back in a few minutes. But that's this should be appreciated. This is not a direct connect. This is not an algebraic relation I've written. This is this is an interpretation here that this is what it is. If that is the case, now that is an interesting feature. Remember, this was a time-like vector. So P alpha will be a time-like vector if m was a constant. Right? So let's do what is P alpha. P alpha. Right? That's going to be the same in every frame. The moment you set momentum is a 3 vector and energy is a time vector associated with that, these are frame dependent quantities. There is no point in talking about what's the energy of a particle. It will be different in different frames, right? Because it's only a component. Momentum, no point in talking about momentum and comparing with a friend because that won't be the same. So you have to talk about something that is invariant with respect to a frame, and then that will be actually the square of this. So that's interesting, right? What is the invariant quantity associated with momentum? What is the invariant quantity associated with energy? That's more fundamental than energy and momentum. So let's find that out. So that's the square of that quantity. And it's off the screen. So the square of that quantity, but that we know how to calculate. Put a negative sign in here and square it, right? And plus p squared. And let's see what that comes out to be. But E over C is by definition this, right? So this is equal to, maybe I should write this down here. So that's E over C. E is equal to mc squared gamma. That's a definition. Momentum is mv gamma. In relative. So this is, put this values in. So this is minus m squared c squared. So this is m squared. This is I'm multiplying that by so m squared c squared gamma squared, right? Minus, or sorry, plus m squared v squared gamma squared. What is that equal to? That's equal to minus m squared c squared gamma squared 1 minus beta squared. Again, the same expression. We know that that's equal to 1. So that's equal to minus m squared c squared. So the invariant quantity is the mass. You don't want to compare momentum or energy. It's the mass that is remaining the same. Does that mean that momentum, if you increase momentum, energy is decreasing? No, because this is a difference in quantity. Okay? This is constant. So what we have learned is, so this is the famous Einstein's equation that if you put this all together, say that energy square is equal to m square c raised to 4 plus p square, p dotted with p square c square. Where is your E is equal to mc square? Right, that's what, say, usually when you write that, in the early days of relativity, there was, it was not very obvious how to put this. So sometimes you said mass changes. So you said, you combined this with a gamma and you said that, oh, this is m prime. So you said this was m prime c square c raised to 4. Where you can, that is this v square over c square, and you can combine that and say how mass changes. But we don't want to put that in the new form. We never say that. Mass is a constant. But then how do you associate that? Go to the rest frame. There's a clear connection in there. So energy in the rest frame will always be equal to mc squared because there is no kinetic energy. Right? Kinetic energy is gone, but still there is an energy associated with mass itself. Like just because you have matter around, that's energy, and that was what became a very crucial event in the sense that that's mass. The moment your mass has energy, that means you can destroy an atom and you can get energy out of it, and that's the idea of an atomic bomb. It led to horrific things, but very nice idea. As far as the idea goes, very cool, but yeah, led to bad things if you want. Yeah, so that's your energy. And now one more thing, I can take a few more time, and you would say, where is kinetic energy then? Right? You would like to see the kinetic energy there, right? Energy we know has kinetic energy in it. So let's put this together. Let's go back to your energy expression, mc squared gamma. Energy is equal to mc squared gamma, right? That's your definition. So that's equal to mc squared over 1 minus v squared over c squared. Oh, Jordan had to leave. Thank you. To see the kinetic energy term, expand this for small velocities. Anyway, v is usually smaller than c, but even if it was close to c, at least we can do a series expansion. And this is mc squared 1. If I do a series expansion, 1 by 2 shows up there. So this is 1 plus 1 by 2 v squared over c squared plus 1 by 2, 1 by 8, I think. 1 by 2 minus 1 by 2, so it's minus 1. So this is minus v raised to 4 over c raised to 4. It's not important. We want output. Okay. So that's equal to, notice the second term is the crucial one. That is still the rest energy. This is the rest mass energy. Just because you have mass, there is energy associated or energy associated with it. Plus, notice the c cancelling out. Crucial because that's a non-relativistic term, kinetic energy, right? Half mv squared, no c in there. Plus higher order terms. If you want, this is 1 over 8 m v raised to 4 over c squared plus higher order terms. And all the higher order terms go to 0 if v was very small compared to speed of light, but still this is there. Right? But then in non-relativistic physics, you never change it. right? Mass remains mass, right? You never try to destroy or it doesn't change at all. So it's a constant, and you usually talk in terms of change in energy, so that doesn't contribute. It never shows up in experiments. Unless you're doing relativistic physics where you're destroying mass somehow, then that comes into picture. And that's atomic bomb. So that's momentum and energy. And let's come back to the acceleration and do some actual problems where we will put a charge in an electric field. How does it look like? Or what is the path it takes? That's what we will ask. Or what do we mean by constant acceleration in relativity? Like the simplest problem in Newtonian physics we do is uniform acceleration. Right? But uniform acceleration, what does that mean now? Because acceleration is a 3-vector number. So we will define what is called a proper acceleration and then talk about what is a particle moving in proper acceleration. Okay, thank you. And thanks for allowing me to take this extra time. It helps a lot. Thank you, Alia.
Could you please repeat it?
No, I just said thank you. Yeah, so thank you for allowing extra time. Yeah.
Excuse me, I have a question.
Oh yes, please.
Yeah. Yes. Do we have to submit homework number 7?
No.
No. Okay. Okay. Thank you.
You can specify a due date for the homework in one. Okay. So, I wanted to make sure I was.
I started to work on it last night. First I had to walk all the notes. Like sometimes I try to write down really quickly his notes, especially in class, and then I can't read it. But yeah, I just read the notes.
I really think if I went through his notes and found every thing in it and submitted that to him, I could just turn nothing in the rest of the class.
Right? That's right. That's a good plan.